Morning, everyone. I'm Namgee from Institute for Theoretical Physics of Ulm University. And firstly, I would like to thank our organizers for the efforts to organize this nice conference. I'm going to talk about this chirality-induced orbital selectivity, but not in details. I will aim to draw your attention onto my topic, and then we can discuss further later on during this conference. So I'm studying enantiospecific transmission of an electron through chiral system. In other words, molecular handedness-dependent electron transmission. So what is the chirality? So let's say we have an object, my left hand, and its mirror image, right hand. If they cannot be superimposed by each other, then this geometric property is called chirality. And this chirality is extremely abundant in biological systems. It's not enough to say abundant. It's basically everywhere. You already saw the graphics of chiral molecules from the previous talks in the magnetoreceptor, photosynthetic system. Amino acids, sugars, DNA, they are predominantly, not all, but predominantly chiral. And one interesting nature of this chirality is that amino acids predominantly possess L configuration, and sugars have D configuration. So there is no mixture of L-alanine and D-alanine in our body. So this is referred to as homochirality. And this example already tells us that there might be a fun physics behind it. So let's go to physics. There was an experiment measuring spin polarization of electrons after propagating through a layer of chiral molecules. So in an experimental setup, we have a gold substrate and we shine UV light. Depending on the polarization of UV light, we can determine the initial spin state of the electron. And then we anchor chiral molecules onto the gold substrate, and the electron propagates through the chiral molecule, and we measure the spin polarization of the electron. When we prepare unpolarized spin state initially, then people figure out that after propagating through the chiral molecule, spin is polarized. This indicates that the chiral molecules play a role as a spin filter or spin polarizer. So we want to know how. How does it happen? We don't know yet. There is no clear explanation, like completely explaining how the cis effect happens. What people have agreed is spin-orbit coupling may play a role here. So there is electron with spin, and it has momentum, so it's moving. And there is electric field generated by partial charges inside the molecule. So the electron can feel an effective magnetic field, and it can interact with spin. So it's reasonable that spin-orbit coupling can induce some kind of spin dynamics. And in the case of spherically symmetric potential, this can be rewritten as dot product of spin operator and orbital angular momentum operator. Now, the issue is the spin-orbit coupling strength generally increases with atomic number. And biomolecules are mostly composed of light atoms like nitrogen, carbon, oxygen, and hydrogen. So spin-orbit coupling strength in biomolecules is too weak to induce appreciable spin dynamics. So it cannot explain the spin polarization obtained in experiments. To overcome the limitations of the weak spin-orbit coupling, people have proposed many, like various physical mechanisms and incorporate them. So for example, electron-electron correlation. So coupling between the propagating electrons and bound electrons inside molecules, and electron-phonon interactions, so coupling with a nuclear vibronic motion, and interfacial effects, the contribution of strong spin-orbit coupling in a metallic substrate, because metallic substrate are composed of heavy atoms. And today I'm going to briefly introduce chirality-induced orbital selectivity, so contribution of orbital angular momentum of the electron. So this is how we model the system. There is transverse confinement given by harmonic potential, and its equilibrium position is conditioned on Z, so longitudinal direction. So it draws a helix, and there's transverse confinement. So collectively, it forms three-dimensional helical electrostatic potential. Now we will send through an electron through this chiral potential. And I'm going to introduce another bosonic operator, C and D. So their number state forms a composite eigenstate of orbital angular momentum operator, here NC and ND. So orbital angular momentum in these spaces is diagonal. So expectation value of orbital angular momentum is given by NC minus ND. So if we look into the Hamiltonian, we can see the linear orbital coupling. So it's a coupling between orbital angular momentum, which is transverse degrees of freedom, and linear momentum in the longitudinal direction. There is coupling between them, which is chiral. The strength beta here, this depends on the radius of a helix and pitch of a helix, and omega, the angular frequency, which is much larger than nuclear vibrating motion because the electron is 1,000 times lighter than nuclei. And this is generally larger than spin-orbit coupling. There's one term with exponential Iz divided by pitch and C minus d theta. This term increases linear momentum by h bar divided by pitch and decrease orbital angular momentum by h bar. And the green term is a Hermitian conjugate. So it decreases linear momentum and increase orbital angular momentum. So there is a coupling between linear momentum and orbital angular momentum. Okay, let's consider a case. So I'm going to prepare initial states, just like spin case, spin up and spin down. Now here it's h bar of orbital angular momentum and minus h bar of orbital angular momentum. And I'm going to consider one transition case, transition to zero orbital angular momentum. So h bar to 0 and minus h bar to 0. And let's compare them and see what happens. So the responsible coupling term is for h bar. It increases linear momentum by exponential IZP. And for minus h bar case, it decreases linear momentum, so exponential minus IZP. And there is C operator, so it decreases orbital angular momentum. And D operator, it increases orbital angular momentum. And if we see the energy, transverse energy, then since the C operator decreases one quantum of NC, so it decreases transverse energy by h bar omega. And D operator also decreases ND by one quantum, so it decreases minus one quantum, so h bar omega. But if we see the longitudinal energy, in the case of h bar case, it is increased, but minus h bar case, it is decreased. So if we think about energy conservation, which is delta EXY plus delta EZ is equal to 0 if energy is conserved, only the h bar case can fulfill this condition because delta EXY has negative value and delta EZ has positive value, so their summation can be 0. But minus h bar case, both have the negative sign, so they cannot fulfill the energy conservation condition. So this results in the preferential transition. So h bar state, initially h bar state tends to transit more to 0, 0 state, and minus h bar less likely to transit to 0, 0 state. And such transition result in the enantiospecific transition. So transmittance depends on the incident OAM state, just like spin. As I explained before, spin up and spin down. If we prepare unpolarized spin state, there is polarization, so there is different transmittance depending on the initial spin state. Analogously here, h bar orbital angular momentum minus h bar orbital angular momentum, they have different transmittance depending on the incident orbital angular momentum state. It's quite fast. So it's already summary. So chirality is abundant in biological system. You can see everywhere for the synthetic system where we were usually interested in, and magnetic receptor. And it shows an enantiospecific electron transmission. I personally expect it might play some role in a biological, maybe metabolism or some biological process, signal transduction. Because there must be a reason why there is homochirality and there's an enantiospecific transmission of an electron. So this cis effect has been observed in many experiments. No matter what chiral molecule you use, alpha helix, DNA, it's been showing in most of cases it shows spin selectivity. But the underlying mechanism remains elusive. So as a theorist, I'm working on this to figure out what's actually happening inside. And we theoretically demonstrated that 3D chiral electrostatic potential can induce significant orbital selectivity. So the electron transmittant depends on the initial OAM state. So this proposed that the orbital dynamics of an electron may contribute to enantiospecific transmission along the spin dynamics.